So yeah, I just want to give a huge thank you to Justice and Pablo for hosting me. I'm really glad to have the privilege of speaking to some of the best and brightest students in the entire country. This talk is going to be geared towards these students, but hopefully others will also find it valuable. And just a little bit of context, I'm going to be talking a little bit about my sort of story and what I've learned about invention and innovation along the way. So a little bit about me. I graduated from UF, go Gators. I had a double major in chemical engineering and physics. Currently, I am the CTO and technical founder of Rain AI. So Rain is an AI hardware company. We're about 40 full-time engineers, and we're building essentially next-generation computer chips for running neural networks. I have 8 patents granted, several more pending on the way, and over 500 citations for my published research. So how did I get here? And what lessons did I learn along the way? That's what I'm going to be talking about. Really, I want to focus on what it takes to create something new in the field of science. So I'm probably going to talk about 4 periods in my journey, starting with my research in UF and ending with today. And after each of those segments, I'm going to touch on some of the lessons that I learned during that period of my life. So my story really starts at UF in 2012. I started doing research in the material science department under Professor Mondino, who would later go on to become one of my co-founders, actually. When I got there, I really wanted to study nanotechnology. That's why I decided to double major in chemical engineering and physics. So I started out studying nanofibers, right? Sort of one-dimensional nanomaterials. Here's a, scanning electron microscope image of some polyequivalent nanowires that we had worked on. But around the same time, in 2012, I also read about what was really a major breakthrough in neural networks. In 2012, they had finally surpassed the state-of-the-art in computer vision, in object recognition. And now we know this as the ImageNet moment because that was the data set that was used. But this was a huge deal because prior to this, scientists couldn't really get neural networks to work. And because of how ubiquitous neural networks are in animal brains and their capabilities, I knew that this was going to be a huge turning point for the field of AI and neuroscience. So I actually started reading books on neuroscience. From my perspective, I really just wanted to understand how the brain worked. And I figured with these recent breakthroughs in neural networks, artificial neural networks, it was really only a matter of time before the two fields kicked off a feedback loop between each other, with one informing the other. And that's something that we're definitely seeing today. So in 2014, probably the most important year for me, I had an idea for combining these two ideas. And the idea was to use these specialized core shell nanowires to connect large numbers of silicon neurons together on a chip. And prior to this, I realized that the main limitations of artificial neural networks was going to be computational resources. And so standard computer architectures like GPUs are actually not really very good at simulating neural networks and certainly not even remotely close to as efficient as real brains. So there's a huge amount of room for improvement in redesigning our computer architectures to make them better at running neural networks. So this was really my attempt to solve this problem. So it was the first patent that I filed, and it would go on to change my life. With Dr. Nino's help, I applied to the National Science Foundation research grant for $250,000 and was ecstatic to find out that I had actually received it. During this whole process, I really thought a lot about what it takes to invent something new. And my biggest takeaway was that being multidisciplinary is a huge advantage for inventing things because you naturally have less competition for new ideas. I mean, if you think about it, if you can master multiple fields, there are fewer people who sit at that intersection. And you also have a larger canvas of ideas for which you can actually combine things together. For a similar reason, staying at the cutting edge is another really big advantage, because people have had naturally less time to explore and exploit these ideas in these very cutting edge fields. And then finally, I really considered how I was spending my time. If you only spend your time learning, then by the time you have a good idea, you really won't have developed the skills necessary to create or design or build. And this can be building simulations of what you're trying to build, sketching, diagrams, building mathematical models. But whatever it is, you have to balance learning and generating new ideas with trying to execute and actually doing things. So, as luck would have it, shortly after my research was published by US Office of Technology Licensing, I got a phone call from a group of investors who were interested in actually commercializing this technology. They started a company called Plasma Chip, and they wanted to own 85% of the company from an initial angel investment of $300,000. I didn't know anything about business at the time, and so I consulted with some professors and other people at the University of Florida, and I realized that this deal was not ideal. So a friend of mine, Gordon Wilson, who would become the third co-founder of Green, along with Juanito, helped me renegotiate with this group of investors. We ended up creating our own company, Green Neuromorphics, and these investors then put in an angel investment for a much more standard 15% into the new company. And then we went to Silicon Valley to seek further venture funding. And I also want to say, during this whole process, I was very lucky to have the help and support of the US Office of Technology Licensing, as well as making it into UF Innovate. These resources at UF were absolutely instrumental in the early success of the company, and I really deeply appreciate it. So in early 2018, this was after dozens of meetings, venture capital people in Silicon Valley, and trips flying out to Silicon Valley for 2 weeks or so, we happened to meet two pretty influential engineers. So Paul was a co-founder of Neuralink, and he was also a neuromorphic engineer, which is the field that we were working in. And Scott Gray was an engineer, a very early engineer at OpenAI. And so in a joint meeting with these two, we laid out our ideas, our vision for the future. And as a result of this meeting, we got a direct introduction and a recommendation actually to Sam. After a 1-hour meeting, Sam decided to invest $1 million into it. And this was to say this was a huge turning point for our company would be a dramatic understatement. There's a quote that luck is where preparation meets opportunity. And well, I don't think this quote is entirely true. Some things are always going to be outside of your control. There is an element of truth to it. You can influence your own luck. And one of the biggest ways as a company is for the company to just stay alive long enough for luck to strike. And I found, after talking with dozens of entrepreneurs, that this is actually really common. And it's a big way that you can influence the future of the company. Just stay alive long enough until something rolls across your desk that you can latch your teeth into. Another way to influence your luck is to leverage every opportunity that you have into 2 more opportunities. So if you make a new valuable connection, ask them for 2 more connections. If you make a big customer win, leverage that win into 2 more customer wins. So the way that I think about this is, I'm an engineer, so I think about it in terms of binary tree. But this is just the nature of exponential growth, right? You want to achieve exponential growth in your network, your connections, and your opportunities. And finally, and probably most importantly, you actually really need to be prepared for when that opportunity comes across your desk. There's no substitute for confidence. Smart people are going to know when you're BSing them. So the most important thing is that you really, really know what you're talking about. So in early 2018, we applied and were accepted into Y Combinator's summer program. At this point, we make the decision to move the company to San Francisco. After our program at Y Combinator, we raised a $5 million seed round and continued our work on developing this technology at Stanford's nanofabrication facility. At this point in time, early 2019, things are going really well. Our initial results are super promising. We end up publishing our work at a very high impact conference in material science. We end up demonstrating the core functionality of the technology with regards to the nanowires. And at the same time, we're building a silicon chip, which is going to serve as essentially the substrate and the interface for these nanowires, which will then, the nanowires will connect all of these nodes of the chip. In late 2019, we get our chip back, and it has a critical bug, and it renders the entire system non-functional. This was less than ideal. Very shortly thereafter, COVID hits, and we're forced out of Stanford's nanofab facility because we had to quarantine. So at this point, we are desperately trying to give up the chip and respin it while dealing with COVID. But the company is basically on life support, and we had to let go of some of our engineers. And this was extremely difficult for me and for the company as a whole. So I want to talk about failure. Failure hurts. This was our first real brush with failure, and it was very hard, and it hurt a lot. But if you're trying to build something new, you're probably going to fail at some point along the way, and it's something you have to accept. Many companies, many of our competitors died at this point. But failure doesn't have to be permanent. And instead of giving up, we took a really critical look at our entire technological approach. You know, the nanowires, it was going to cost so much to scale this technology up. And the time to market was going to be so slow that we really had to take a hard look at that for the approach that we were taking. So we ended up with a strategy that would eventually bring us back from the brink of death. I want to talk a little bit about avoiding failure, because that's the ideal scenario, is that you don't get into that situation in the first place. The biggest one is don't stack risks. Especially don't combine two technological risks. This might seem obvious, but it's actually really easy to get in the headspace of where you're lumping two different technical challenges into one and not really realizing that these form a chain. And especially when you start chaining risks, that's when your rate of failure goes up. Right? Another thing is, don't assume that one challenge is going to be easy just because it's easier than something else that you're trying to do. For example, the nanowires were the riskiest part of our initial endeavor. But it ended up being the silicon chip that failed, which should have been easier. But that didn't mean that it was easy. And we were relying on both in order to succeed. Right? So be very careful in situations where this has to go right, and this has to go right, and this has to go right, and then you can be successful. And then the last thing that I'll say is avoid going to market with more than one major risk, whether that be technical, business, or customer. So if you have a large amount of technical risk, don't enter an unproven market. So after this period, we started asking ourselves two questions. One, how can we go to market faster and with less risk? And two, what is really at the heart of what we're trying to build here? And the problem is we were trying to solve two problems. It's really what I just mentioned. We were trying to build a new type of computer architecture that was designed for neural networks. And we were trying to develop a new type of memory device that was based on nanowires. So really, we took a look at the nanowires and we realized that because of the huge capital investment required to scale the manufacturing process and the reliability challenges we were still struggling with, we would decide to focus on developing the computer architecture itself and to use standard memory technologies, but in a way that still embodies the core of what we were trying to do. So we would use an approach which was always at the heart of the company, which was compute in memory. But now we would try and do the same thing but using SRAM, which is also known as cache memory. And so the idea is that the biggest difference between biological brains and the way that normal computers work is that as opposed to conventional computer architectures, which they separate memory and processing. You have a memory chip over here, and then you've got a CPU over here, and you have to move all of that data back and forth constantly across this very narrow bus. But in brains, the same thing that stores the memory, the synapses, that's also where computation happens. And so what we would try to do is we would try to use SRAM to do computation in memory. But we're not the first people to think of this. And the general idea had been attempted in the past before. But we were, again, really lucky that there was new research that had just started to come out that showed that there was a very promising path forward for this approach, and we decided to run with it. So, fast forward to today, and we've designed a new SRAM-based compute memory array, which achieves the highest efficiency matrix multiplication that's currently on the market. And we're super excited about this. Since matrix multiplication is the most important operation in running any kind of AI or neural network, this memory array can serve as the core of an entirely new class of AI accelerators. So we've taped out this design at the world's leading foundry, TSMC, in their 6nm fab, and we're getting our test chips back essentially in another month. So we spent a long time designing, developing this, sending the design over to TSMC, and we'll finally get results back. And we have done very extensive detailed simulations on performance characteristics of the system. So just to briefly summarize, what have I learned about invention, about innovation? Well, it's really hard, and I'm sure you've heard that from every speaker up here today, but it really truly is incredibly difficult. But a few other things too. The first is, at least what I believe, be multidisciplinary. If you really want to innovate, the more fields that you master, the larger the canvas that you'll have to create new things, the less competition you'll have in that domain. Stay on the cutting edge of research. Something that I think is really important is being able to differentiate between the pop sci incremental advances that you see every month or two, science, popular science publications and things like that, and the actual real genuine breakthroughs in science. And those are rare, but when they happen, that's where you want to put all your chips. You want to focus your effort on learning and applying those. Always be multiplying your opportunities, leverage your successes into more successes, and failure hurts, but don't give up. So now, we're raising our Series B. We're going to have our first test hardware available in early 2025. Thank you so much for your time. Feel free to reach out, send me an email to just say hello or inquire about what we're doing.
Thank you so much, Jack. Good man. I want to give an opportunity if a few people have any questions. Awesome, perfect. Firing away today. That's good. Hey, the curious mind usually makes the most fun. I bet I'm cool.
Hey, my name is Jerome. Nice to meet you. Appreciate you. You're an engineer. I'm an engineer as well. I feel like a problem with, at least for me, is I try to be too exact in what I'm doing. And obviously working with nanofibrers, you have to be exact. And when you're developing that first stage of the product, how exact are you, and how do you stop yourself from trying to make the product perfect the first try?
That's a really great question, and I think I don't really have the personality of like exactness. My professor one, is a very precise type of person, but I think somebody mentioned something along these lines. Don't let perfect be the enemy of good enough. That's a philosophy that I like to live by. And really, when you want to do, this comes into play with the advice on doing, building, experimenting. It's really not possible to make anything perfect when you design it the first time. And you've just got to keep iterating, and when you have a component that is functioning well, and it's got testable results and you're happy with it, move on to the next piece. But really, that philosophy of don't let perfect be the enemy of good enough is, I think, the best advice.
When it comes to the theory portion of it,
Yeah.
how do I make that more practical? Like, for instance, I'm calculating the lift that the wings are generating. How, when I see the deviation from theoretical to practical, how do you deal with that?
That's part of the iteration and refinement process. So deviations like that, you just have to understand where your model is going wrong, and really try and pinpoint. That's where the other half, I think, comes in, which is like not necessarily building, but just learning, right? You've got to learn, like, other people have probably run into the same problem before, and that's why I think like basic science as a whole is so important, because I cannot tell you how many times I have had a super obscure issue and been like, I'm gonna go and see if maybe somebody's figured something out about this before. I reach into the literature, and lo and behold, some obscure researcher, at some university has actually done work on this problem, or at least given me a foothold into it. So you've got to really understand exactly what's going wrong in your model and why it's not lining up with the data that you're getting. And usually that's because you're not modeling something. It's not always practical to model every little piece of a problem, but if it's important, you've got to include it, and you've got to figure out exactly why that deviation is occurring. So that's how I think about it, is in terms of iteration. You're always trying to improve.
Any other questions?
Hi, great presentation. You mentioned going to Y Combinator. I'm planning on applying in November. Could you kind of like walk through that process and what you felt like it did for you?
Yeah, Y Combinator was a transformational experience for me in terms of just like being a crash course into how to run a business and what's important in business. The process is like, what I'll tell you, a piece of advice is that they really care about growth metrics, right? That's what they really care about at the end of the day. If you've shown progress, whether that be in terms of the customers that you've acquired over the past year, like year-over-year growth, or if you've had some really impressive technical milestones, that's really what they're looking for. And so the other thing that they absolutely drill into in YC is, and again, this has been talked about today, closing that customer feedback loop. You have to talk to your customers, the people that are going to be your potential customers. You have to understand what they care about. You have to give them a version of what you're trying to build, and then watch them use it and see how are they actually using it, how is it different from what you expected, and learn from that, iterate on that, and get feedback from the customer. So those are some of the most important things that they really try to do.
And sorry, if I have one more question. Yeah. So with your company that was obviously more technical, and you guys are just launching your customer chips now, how were you able to get that customer feedback before actually having the customers?
Yeah, we built some initial prototypes. We built some early prototypes, we collected data from them, and we built simulations that showed how the technology could scale. And so that combination, plus a lot of the experts that we had talked to, we had talked to a lot of researchers and experts in the field and gotten their sort of vote of confidence, and that certainly helped.
Thank you.
One more? Could we get the slide deck?
For rain? Yeah, sure, I don't see why not.
All right, that was super quick, so I'll give it to Jeff.
Great presentation. I loved what you talked about with failure and how a lot of founders face these really critical moments where everything looks like it's crashing down around them, and you have to have that calm composure to find the best exit when it doesn't look like there's any. So what are some of the things that you did to steady yourself and your team to find what you needed to do next and keep the level headed?
I mean, it really boils down to, I think, two seemingly contradictory things. You have to appear confident. You have to carry yourself in a way that, you know what you're doing, right? You know what you're talking about. That's really difficult because the way that you have to act is actually completely different. The way that you have to act is with this extreme sense of urgency and almost be frenetic in how, founder mode has been brought up. That's really what it is, working super long hours and being willing to get into the weeds and do whatever it takes to fix whatever problems you have. It's definitely a very high stress. And you have to sort of act in a high stress way. But on the outside, for your team members, you've got to keep it together and be like, okay, we're going to get through this.
Thank you.
Awesome. Give it up for Jack one more time. Pablo, get up here.